Up until this point in AP Physics 1, we've really been focused on describing motion, explaining motion, and being able to predict different kinds of motion. If you think about it, we've talked about one-dimensional motion, horizontal motion, or dropping objects, so that's like vertical one-dimensional motion. We talked about two-dimensional motion with projectiles and launching objects. We talked about uniform circular motion, so things that follow a circular path, whether it's a vertical circular path or a horizontal circular path at a constant speed. In our last unit, we just got done talking about rotational motion. How do we describe and make predictions about objects that can spin? In this unit, we're going to be focusing on our last different kind of motion. And one of the examples is this right here. We've got a 500-gram mass hanging on a string. It's attached to a pivot point right here. And right now, this thing is in equilibrium. The force of gravity pulling down is balanced by the force of tension pulling up. They're the same size, which is why this thing is at rest. So it's kind of like an equilibrium position. And if I just take this thing and pull it back a little bit from its equilibrium position, let go, this thing swings back and forth, just like you on a swing, or any mass attached to like either a solid thing or a string that can pivot, it's just going to swing back and forth. And what's different about this motion compared to the things that we've studied is there's just the same cycle or the same pattern happening over and over and over again. We call this periodic motion. If you remember the word, we'd used the word period before to talk about like the period of orbit, like how long it takes a planet to orbit a star, or how long it takes a satellite to orbit a planet. That's called its period of orbit. Well, we could talk about the period of oscillation with this pendulum system, how long it takes to go from, let's say, this point back to that same point again. So we could use a stopwatch and we could start it and stop it, and that stopwatch would tell us how much time it took to go from one position back to the same position again, and we call that the period of oscillation. So the question is, like, what might affect the period of oscillation of a pendulum system? Well, if we look at this system, we could change a couple different things about it. We could change the mass that's hanging on the end of the string. We could change the length of the string of the pendulum. Or, if we're starting this from rest, we could pull it back a little bit and let it go, and let it oscillate or swing back and forth. Or we start from rest, we could pull it back farther and let it go, and maybe that would affect how much time it takes to go out and come back, one period of oscillation. So we're just going to do 3 quick little experiments to find out, like, how do each of those things affect the period, or do they not affect the period? So let's first do our test of mass. We're going to change the mass hanging on the end of the string and find out how it affects the period. And so if we're going to change the mass, we're actually going to do a little comparison. I'm going to hang 2 masses on here. One 500 grams, and the other one is 1,000 grams, so it's double the mass. And I'm going to use the same length string, and I'm going to pull them back the same amount. And so we're just going to really quickly compare visually which one takes less time or more time to swing the distance, or do they take the same time. So changing the mass with the same length and the same amount that we pull it back. Okay, you can see pretty clearly that the one with twice the mass really took the same amount of time to swing out and swing back, so they have the same period of oscillation. And so apparently, mass doesn't affect the period. Well, let's find out what effect length has. So if we're going to change the length, I'll have this length string, and then we'll use a shorter string. And we just saw that mass has no effect on the period, but just for our investigation, I've got the same mass, 500 grams, one hanging on a short string. And when we talk about the length of the pendulum, it's the length from the pivot point to the center of mass. So this would be our length L of our pendulum. For this one, it would be from the pivot point to its center of mass. And so I'm going to pull these things back and find out how much time it takes for one period of oscillation. Okay, and we can see that the shorter length has a smaller period, and the longer length has a larger period. So it seems like as length increases for a pendulum, so does the period of oscillation. So our last experiment, let's find out how changing the initial angle that we pull it back affects the period of oscillation. So now we're back to the same length string, the same mass hanging on the end, and now I'm going to pull one back a little bit and pull the second one back considerably more. Let's find out. Okay. It should be pretty clear that in each of these cases, they have the same amount of time to go out and come back, so that they have the same period of oscillation. So apparently, you put one back a little bit or one back farther, it really doesn't affect the period of oscillation. So when we're talking about the period of a pendulum system, mass has no effect. How far you pull it back has no effect. The only thing that we've been able to see is the length of the pendulum affects it. Now, we need to talk about one more thing, because this is not within our ability to change, but if I pull this thing back, why does it like increase speed and decrease speed? Why does it speed up and slow down, speed up and slow down, speed up and slow down? Well, there's something to do with the force of gravity. Gravity is causing it to accelerate, speed up as it approaches the bottom part and slow down as it approaches like the top part on the other side of the swing. And so gravity is causing this acceleration. So if this had a larger acceleration due to the force of gravity, it would take less time to complete one full swing. Well, what could possibly change the acceleration that something experiences due to gravity? Well, it's based on the Earth's gravitational field strength. If the gravitational field strength of the Earth or a planet increased, this pendulum would have a larger acceleration and would take less time to swing out and to swing back. And so even though that's not an experiment we can do here on Earth, we can see that if the gravitational field strength of a planet goes up that you're on, then we would expect the amount of time to go out and back to decrease. And so as g increases, little g increases, the period would go down. So it turns out that the equation that we use to predict the period of a pendulum system depends on the length, and it depends on the gravitational field strength. It's the period of a pendulum system is equal to 2 pi times the square root of the length divided by the gravitational field strength. And this is an equation that you have on your AP equation sheet.